All right, this is problem 521 from Smith Van Ness, 8th edition. We have 1 mole of an ideal gas with Cp 7/2 R and Cv 5/2 R. It's compressed adiabatically in a piston cylinder device from 2 bar and 25 degrees C to 7 bar. This process is irreversible and requires 35% more work than a reversible process from the same initial state to the same final pressure. What is the entropy change in the gas? So what we've got here, a couple things that we should note. First of all, this is a closed system, and it's an ideal gas, of course. We're given some information about the properties here. The compression, it's an irreversible adiabatic compression. So irreversible adiabatic compression. We start at state 1, P1 equals 2 bar, T1 equals, remember it's 298 Kelvin. All right, and then we go to state 2, and we are told that P2 is 7 bar. Notice we don't know anything about T2. We don't know anything about the molar volume or the total volume here. If we want, we can calculate V1. We'll leave that blank if we want to do that. All right. So we also know, of course, that the process is irreversible. It requires 35% more work than a reversible adiabatic compression. That's accomplishing the same state. That's important. A reversible adiabatic compression from the same initial state to the same final pressure. What we want to find delta S for the gas, right? And this is delta S for our system. Okay, so we want to find delta S of the gas. First thing that I would probably do in that case is I would go to the equation in my textbook where we calculate the delta S for a gas, for an ideal gas process, and we get delta S is equal to Cp natural log of T2 over T1 minus R natural log of P2 over P1. That looks like the best place to start. The problem is, if you look at this, we're wanting to find delta S of our gas, right? We're told that the process is irreversible, that the real process, now when we calculate the entropy of the gas, this is of the irreversible process. We're told this is an irreversible process. The question is, does this equation apply to an irreversible process? Because if you look at the text, you'll see that this equation was derived for a reversible ideal gas process. But remember what we talked about in class. We talked about the fact that even after we derive this equation for a reversible ideal gas process, all of these parameters in here are state functions. Delta S is a state function as well. And so this equation applies to both irreversible and reversible processes. So that's good. That's a sign that we're at least partly on the right track, but there's another problem. The other problem that you probably have seen is that we do not know, while we know P1 and P2, in T1 we do not know what T2 is. We don't know what T2 is. So T2 is unknown. That means we can't solve this equation for delta S. We have one equation, two unknowns. So what are we going to be able to do? Well, another naive assumption would be, well, let's go back to chapter 3. There are some equations for reversible adiabatic processes where you can relate P1 T1 to P2 T2, or P1 V1 to P2 V2, V1 T1 and V2 T2. Are those equations valid? The answer to that is no, those equations are not valid, because those equations were derived for a reversible process. So that kind of leaves us in a bind. What can we do? What can we do for this? Well, what we can do is we have one more equation that we can still use, and that's the first law of thermodynamics. Right? That's the first law of thermodynamics, and that says that du is equal to dq plus dw. Does this law apply? Yes, this law applies. It's a closed system. This is the first law for a closed system. Right? Does this apply for an irreversible adiabatic process? The answer is yes. The first law doesn't matter. Whether it's reversible or irreversible, it still applies. All right? How can we simplify this? Well, we know for our real process, which is irreversible and adiabatic, what does that mean? That means there's no heat flow. There's no heat flow to or from our gas. And so our first law applied to our system, this is equal to 0. And we're left with du is equal to dw. Now, if this were reversible, we could start to put in integral of minus pdv, but this is irreversible, so I'm going to write irreversible here. So this is not equal to minus pdv, but we can still integrate this, right? So let's integrate this. We integrate du, we get delta u, right? We integrate dw, and remember, we integrate dq, we get q. We integrate dw, we get w. This is irreversible, right? So delta u is equal to work for the irreversible process. All right, so where's that going to get us? Well, what is delta u equal to? Delta u is equal to CV the integral is CV dt. So that's equal to the integral from T1 to T2 of CV dt. So what this is saying is we want to find the entropy change in the gas. So we need to kind of step back and think of what we're doing. We did a little bit of derivation here, but where does this get us? Our whole idea is to get T2 for the real process. Right? We need to find T2 for the real process. So I should write for the irreversible process. All right? I've got an equation here. If I were to write, if I can write this, this is barely legible, but the irreversible work is equal to CV dt for, is equal to CV times delta T, where we have the irreversible, the temperatures for the irreversible process. This equation is valid, right? Because this is a state function, right? Our work is equal to a state function. So what we can do, if we can somehow calculate the irreversible work, we should be able, right here, the irreversible work is equal to CV times T2 irreversible minus T1 irreversible, right? And notice that T1 is the same whether it's reversible or irreversible. T2, though, is going to be different. So if we can calculate the irreversible work, we can calculate T2 for the irreversible process, plug that in, and calculate delta S for the irreversible process. But that still leaves us, well, how do we calculate the work for the irreversible process? And that's where we bring in this information here. The process, the real process, the irreversible process, requires 35% more work than reversible adiabatic compression from the same initial state to the same final pressure. So what this is saying is that we need to then calculate the work for the reversible process for same initial state and same final pressure, same P2. So the reversible work for the same initial state and same final pressure. So that's going to mean what? What is that going to mean? Well, there's a couple ways to approach this, but the way that I think about it is if I have a reversible adiabatic process, what is that? There's another word for that. A reversible adiabatic process is the same thing as an isentropic process. What does isentropic mean? Isentropic means delta S is equal to 0. All right. So if I have delta S equal to 0, that should be able, that's the equivalent of, or I should say, having delta S equal 0 means that we can calculate the reversible. We are calculating a process of when we calculate the work, it is for a reversible adiabatic process. All right, so what we can do then is we can say, okay, let's take delta S for an isentropic process. That's equal to 0, and that is, we're still dealing with an ideal gas, so we can put this equation in. This is Cp natural log of T2. This is for a reversible process over T1. Remember, it's T1 is the same no matter what. Minus R natural log of P2 for the reversible process. Remember, they both go to the same final pressure, and they both start at the same initial pressure. All right. So I set that equal to, and that's equal to 0. So I can Cp natural log of T2 over T1 is equal to R natural log of P2 over P1. And I want to solve for T2. I can go through a little bit of algebra, and what I get is I get T2 is equal to T1 times the ratio of P2 over P1, and then it's raised to the R over Cp. And what you'll find, this equation is essentially the same equation that you find in, I believe it's equation 323. You have several equations for a reversible adiabatic process. We just took that reversible adiabatic being isentropic, used the equation we derived here in chapter 5, and we got the same equation that was derived for you in chapter 3.23. And you would have been fine on a quiz or exam. You would have been fine just going straight to that formula. But then we put these numbers in. That's 298 Kelvin, and then that is 7 bar over 2 bar, and R over Cp, that's R over 7/2 R, and so that's going to be raised to the 2/7 power. So make sure that you punch those numbers into your calculator correctly, And T2, I forgot the reversible, T2 reversible, that is going to be equal to 426.46 Kelvin, 426.5 Kelvin. So that's my intermediate value. Make sure you include your units. That's my intermediate value in this calculation. This is T2 for a reversible process. So what does that mean? Well, that means I can calculate the work for a reversible process. The work for a reversible adiabatic process, we can go back to chapter 3, or we can realize that we just derived it, whether it's irreversible or reversible, we just derived it here. The work for a reversible process is equal to CV times T2 reversible minus T1. And because T1 is the same for everything, we'll just leave it like that. And so that is 5/2 times R, which is 8.314 joules per mole Kelvin. And this is T2 reversible, 426.46 Kelvin minus T1 is 298 Kelvin. And I calculate that will be 2667. And that's joules per mole. Again, make sure you keep track of your units. That's my answer there. So my kelvins are going to cancel out and just left with joules per mole. So this is the reversible work. All right. This is a reversible work. I want to calculate the irreversible work. We're given some information. Requires 35% more work than the reversible work. So that's 1.35 times the reversible work. We plug that in. The irreversible work, 1.35 times the reversible work. That is equal to 3,600.5 joules per mole. So that's the irreversible work. Now what I can do is I can take that, plug that in there. I can solve for T2 irreversible. All right, so T2 irreversible is equal to what? It's equal to the irreversible work divided by CV plus T1. And so I plug that in. That will give me 471.4 Kelvin. 471.4. Notice that's a lot higher than our reversible. All right, that's a lot different. Okay, so now I know my irreversible, my action, and I've written reversible and irreversible. Sometimes I like to use reversible and real. I like to say real instead of irreversible. So now I can calculate delta S for the irreversible process. And that's CP natural log T2 over T1 for the irreversible minus R natural log P2 over P1. And we plug those in. That is 7/2 times 8.314 joules per mole Kelvin times natural log 471.4 divided by 298. The kelvins will cancel. Minus 8.314 joules per mole Kelvin times natural log of 7 bar over 2 bar. All right, so everything inside the units, or is inside the log operators, units are going to cancel. That's good. joules per mole Kelvin, joules per mole Kelvin. Those are the units of the of entropy. And so we get delta S for the irreversible process. Punch those numbers in our calculator. We get 2.91 joules per mole Kelvin. That's our final answer. That is greater than or equal to 0, right? Is that okay? Yep, that's fine. It's a compression process. Does it have to be greater than or equal to 0? The answer is, well, it is for this compression, but because we're only dealing with the system, right, it doesn't have to be greater than or equal to 0. We could have had a problem where the delta S was negative for our system, and then if you had calculated the delta S for the surroundings, it would have more than canceled that out to have an overall delta S. But here, having delta S being positive is fine, and that's our answer. So this was not a very straightforward problem, but if you take things step by step, you can figure out kind of what you need to do to solve the problem. You look at the problem, it throws you for a loop by saying it's an irreversible process, but it gives you this information about 35% more work required than a reversible adiabatic. One thing that's really important is that this reversible adiabatic, that's one of the big keywords, big key engineering words that you should know. Anytime you see reversible and adiabatic, that should mean isentropic, and isentropic means delta S is equal to 0, and that is equivalent to the doing the work as a completely reversible process, of course. So once we realize that, we can use that information. We wrote this down so we could see where we need to go. We need to calculate T2 so we can calculate delta S, but unfortunately T2 was unknown. We realized that for a irreversible process or adiabatic process, whether it's reversible or irreversible, this equation is valid. Again, that is covered in chapter 3 if you want to go back and review that. And so we went through and we found what the temperature would be for the reversible process. Again, we used the equation in chapter 5 to derive that, but you could have just gone right back to equation 323 for a reversible adiabatic process and got the same answer. We then calculated the work for that reversible process, multiplied it by 1.35 to get the actual work, and then again used this equation to solve for the real temperature, the real final temperature, and then again use our chapter 5 equation for delta S for an ideal gas to calculate the actual entropy change.